All right, hello. Is the mic on? Everything working? We're online? All right, well, welcome back to Data 100. I do apologize for the room being locked. I'm not exactly sure why the room was locked today and not yesterday and hasn't been locked for the entire rest of summer, but we're in here now, and that's what matters. Today I'm going to be talking to you about gradient descent, and so far we've talked about fitting models to data, and the way that we fit models to data is by minimizing the loss. And we talked about how to minimize the loss by taking the derivative, or the gradient of a loss function, and setting that derivative equal to 0, and then solving for the model weights that we want to set in order to achieve the minimum loss. And I mentioned to you yesterday and before that it turns out that oftentimes, even though we can find the solution mathematically, the solution may be really slow to run on the computer. Or for other cases, there might not be a mathematical solution to minimize the loss, and so we need to use some other technique to do so. And so today we're going to be talking about gradient descent. And by the end of this lecture, you'll know gradient descent, which is like the algorithm that people use these days to fit models to data. And hopefully, it'll open some doors for you in terms of the types of models that you can fit. All right. As a reminder, homework 4 is due today, and homework 5 is going to be released today, or rather, I think sometime this afternoon is what we're aiming for, and it'll be due on Friday. Okay, so homework 4, make sure you turn that into Gradescope, and make sure you label all your pages. If you remember from the past homeworks, a lot of people did not label their pages, they didn't mark which questions were for which pages. And if you do that, you'll get a 0 on the homework, so make sure you do label those pages. If you do get a 0, though, don't worry about it too much because you can submit a regrade request and get those pages graded. But it'll just be easier for you and easier for all of us if you just mark down which pages are for what when you submit your assignment on Gradescope. Okay. Homework 5 is going to be a programming assignment, so it's not going to be as math-oriented. There will be a lot of Python, but I believe there will be some math to it. Okay. So we'll be back to programming assignments from now on. All right. So again, our modeling pipeline involves picking a model, picking a loss function, and then fitting that model to our loss function by minimizing the loss. Okay. And before we fit the model by taking the derivative, setting it to equal to 0, and then solving for the parameters, it doesn't work out for complicated models or for complicated loss functions. Okay, so even the simple linear model with the mean squared error, which is the one level removed from the constant model, even that simple case has really complicated algebra or relatively complicated algebra. And if you extend that to multivariable linear models or other types of models, the math just gets really, really hairy and really hard to work with. All right, so today we're going to be learning gradient descent, which is the one algorithm to rule them all, so to speak. It is not the perfect algorithm, but it is probably the best algorithm that we know of today. So it's used all over the world today to fit models. More specifically, it's the primary model of choice for fitting neural networks for deep learning. So it turns out to be pretty popular and pretty useful generally. Okay, so I briefly mentioned taking the gradient yesterday, but I did want to go through a little more slowly what a gradient is, so you can get a better intuitive sense for what the gradient actually means. So if you've taken a calc class, you'll be familiar with the derivative, which is the slope at a particular point on the graph, or a function f. All right? And in this class, oftentimes the interpretation we'll use for the derivative is instead of saying that it's the slope at a particular point, we'll interpret it as if I nudge the x value, how does the y value change? All right? So in this particular case here, if I nudge x to the left, I can guess that my function will decrease. And if I nudge x to the right, I can guess that my function will increase because this derivative here has a positive slope. Because that's kind of the intuitive idea behind a derivative, and it's the perspective that we'll be making the most use of today. Okay, so I'm going to show you a little demo here, and hopefully this works. Okay, so the blue line is a function f, and it has some squiggles, all right? And the red line is the slope at a particular point, which is labeled in purple. I can drag the slider around to move the point. And you can see here that the slope is positive, and the slope is 0, and the slope is negative, and the slope is 0, and the slope is positive. Okay. So that's what you should have seen in the calc class. And we'll move on now to the gradient. And the gradient is essentially the derivative, but for multivariable functions. Okay. So in this class, we've talked about multivariable functions. We've talked about this multivariable function, which is the multivariable linear model. So instead of having only one x value, there are multiple x values, and each of those x values changes the function f. So if you want to find the derivative, so to speak, for this type of function f, one intuitive idea that we can do is pretend that the multivariable function is univariable. So in this case, we'll pretend that x1 is the only variable that changes, and we'll pretend that all the other x2, x3, so on and so forth are not changing. And then we'll take the derivative as though everything else was a constant. And this is what we call a partial derivative. It's essentially, you take the function that has multiple variables, you pretend that all the variables don't exist except for one of them, and then you take the derivative with respect to that variable. That's the partial derivative. Okay, so in this particular case, if I take the partial derivative of this function f with respect to x sub 1, everything else becomes 0 because it's a constant, and x sub 1 here is we take the derivative of this term, which becomes theta sub 1. So that's the partial derivative. Similarly, if I take the partial derivative with respect to theta sub 0, this becomes just a number 1, because the partial derivative of theta sub 0 is 1, and the partial derivative of all the other terms is 0. Are there any questions about doing partial derivatives here? Okay. Let me show you a demo again. Okay, so I have here a multivariable function, and in general, so this is a 3D function, right? It's a function that takes in two parameters, x and y, and outputs a single number. And so what happens is we say this axis right here is the x-axis, this bottom one here. The one pointing off to your right is the y-axis. Okay, and then this one pointing straight up towards the ceiling here is the height of the function in that particular combo of x and y. Okay, so just like how a function in 2 dimensions is a line, a function in 3 dimensions is a surface. Okay, a function in 4 dimensions is like a hypersurface. So in general, if you go beyond what you can visualize, we call it like a hyperblank. So you might hear like hyperplane, like hypercube, or hypersphere. That essentially just means like a 3D sphere, but with more dimensions. Okay. Now, what we'll do for this function here is taking the partial derivative with respect to x here, essentially says let's rotate the y-axis until it points straight out of the page. All right, so I'm going to rotate my y-axis. It's not make this 0, okay, and then rotate my y-axis so it points straight out of the page. And then we're going to pretend that the y is constant. So let's say it's just a value 1. 2. Okay, 2 is fine, and I have to turn this down. So I have to turn. Dang it. I think I rotated the wrong way. Let's try this. This is totally experimental. All right, here we go. So if I rotate my 3D plot so that it looks 2D, this looks like a regular, like one-dimensional function, right? And so the partial derivative here is rotating the axes until one of them points straight out of the page, and then taking the partial derivative at that particular point. Okay, you can also imagine me doing the same thing with the other axis, right? So if I rotate the other axis so that it points straight out of the page, unfortunately here it's like I can't collapse this to one dimension. Actually, maybe I can. Let's try y squared, and then changing this to a 2. Okay, so it's not perfect, but here the idea is like if I treat x like a constant, then this function looks like a quadratic. And taking the partial derivative with respect to y is like rotating my axes until I get like what looks to me like a single variable function. Okay, so kind of the visual intuition behind the partial derivative is that if you have a multivariable function, what you can do is you can kind of get rid of the other dimensions. You can pretend the other dimensions don't exist, and then just take your derivative as normal. Okay. And so the gradient is like the multidimensional version of the derivative. Okay. The gradient is a vector-valued function, which means it always outputs a vector. And what we'll say is if we have a function f that depends on parameters theta, and here I've bolded theta to say that it's a vector, we'll say we can take the gradient of f with respect to theta, which is a vector of values. Okay, so this is analogous to saying we'll take the derivative of f of x, where x is a single scalar. This is like we'll take the derivative of f of theta, where theta is a vector. Okay, and the gradient of f with respect to theta is itself a vector, and every component of that vector is the partial derivative with respect to that component of theta. So in other words, if I take the gradient of f with respect to theta, I'm going to take the partial derivative of f with respect to theta 0, put that in the top slot, take the partial derivative with respect to theta 1, put that in the second slot, so on and so forth. Okay, so it's just all the partial derivatives stacked on top of each other. That's the gradient. Okay, so the interpretation of the gradient is it essentially gives you the slope of a function at any particular point, even though there are multiple dimensions. Okay, so just like how you can plug in a value into the derivative to get the tangent line, you can plug in values into the gradient to get a tangent plane. All right, so how about you try it out? So here I have a function f of theta and x. Take the gradient of f with respect to theta, and then take the gradient with respect to x. And you should write your answers in vector form at the end. So try it out. Okay, so when I ask you to take the gradient of some function and you're confused as to how to actually do the gradient, one thing you can do is expand out the vector dot product into the sum of some scalars. All right, so we know that theta dot product x is theta 0 times x0 plus all the rest of the terms, and then theta p times xp. Okay, so now that we have our function in this form, we can now take some partial derivatives. All right, so we can take the partial derivative with respect to theta 0, which is x0. And so what I'll do is I'll write down the gradient of f is a vector with all the partial derivatives. the first partial derivative, you'll notice here, is x sub 0, because all the other terms do not have theta sub 0. The second term here is x sub 1. The third term is x sub 2, so on and so forth until we get to the last term here. And so what happens is we get this vector that comes out after you take the partial derivatives and stack them together. And you may notice here that this vector here is simply a vector x. Okay, so usually what happens is when you take the gradient of a vector function, once you actually expand out the multiplication and take the terms and do the gradients and stack them on top of each other, you'll get something that looks pretty simple. Usually, not always, but usually, in this class at least, you'll get something that looks relatively simple. Okay, now you can do it with respect to x as well, and by similar argument, right? So the gradient with respect to x is very similar to the gradient with respect to theta. It's just that instead of x's here in this final vector, you're going to get thetas. And so we have the gradient with respect to x is equal to the vector theta. Okay. And now you may notice here, I do want to point out that taking the gradient looks kind of like taking a normal derivative, right? So if I take, so this right here is theta times x, and if I take the gradient with respect to x, I get theta. And this looks pretty similar to a regular function, which is a times x, taking the partial derivative with respect to x equals a. Right? So this transformation here looks very similar to this transformation here. Okay? And it turns out that this happens quite a bit. So the gradient, again, because it extends the derivative to multiple dimensions, a lot of the transformations that the gradient does looks very similar to the transformations that a derivative does. But you cannot always just assume that. What you should do is you should always assemble this vector of partial derivatives and then go through the process of taking the partial derivatives. The reason why I say that is because the rules don't always apply. Okay, so with vectors and matrices, you're going to have transposes and inverses and different types of multiplications. All right, and so because of that, the rules that normally apply for derivatives don't translate directly. But most of the time, you'll get something that looks pretty close. And in this case, it looks very close. Okay. So we're going to be taking gradients of loss functions for the rest of today's lecture. And again, we interpret the slope of a function as saying, if I nudge x to the left or right, how will my function change? And you can also make an analogous interpretation for gradients. You can interpret the gradient of a loss function as saying, if I nudge the first model weight, what happens to my loss? If I nudge a second model weight, what happens to my loss? So on and so forth. Okay, so the way you can interpret the gradient is it says it's a vector that tells you how nudging each model weight changes the loss. Also, because the gradient is a generalization of a derivative, I'm just going to use the word gradient from now on instead of derivative. Okay, so even if the function is single variable, I'll just say let's take the gradient of that function. It's not technically right, but it'll just help us not have to work with a lot of vocabulary words. And also gradient is easier for me to say than derivative. Okay. Are there any questions about gradients before we move on to using gradients? Okay. All right, so now we can talk about gradient descent. Okay, so the idea here is the gradient tells us some useful information about our function f. Did I miss a slide? I did one more slide. Okay. So again, our goal is to fit a model by minimizing loss. And the loss is a function of model weights. Because the loss is a function of model weights, we can interpret the gradient as some indicator of how the model weights should change to make the loss smaller than it was before. Okay. Let's see here. Up on the plot on my left, I have the MSE loss for a constant model. And I've shown you that if I set theta equal to 12, the loss is value 10. So this right here is a loss curve. And if theta is 12, notice that the gradient is negative. The slope of that function at that particular point is negative. Okay? The slope is negative, and we want theta, so we want the loss to be as small as possible, which means we want to nudge theta to the right-hand side. Okay, so keep that in mind. On this plot, if I happen to have this theta over here, notice that the gradient is positive, and we want to nudge theta to the left-hand side. We want to make theta more negative than it was before. Okay. So intuitively, if we have a negative gradient, we want to move theta in the positive direction. If you have a positive gradient, you want to move theta in the negative direction. And so the intuition here is that we can move theta in the negative direction of the gradient. Okay, so if we notice that the gradient is negative, we can nudge theta to the positive direction. We can move it to the right. If the gradient here is positive, we can nudge theta in the negative direction. We can move it to the left. Yeah, Matt?
When you say nudge theta, you mean adding just like the positive or negative scalar to the whole vector element by element? Or?
Yeah, so in this case, theta is just a single number. So right here, theta is simply the value 17, let's say. And I can make the loss negative by moving theta towards 16, or maybe 15. Similarly here, theta is the value 12, and I can make the loss smaller by making theta like 13 or 14. So the idea is that the gradient tells us the direction in which we want theta to move. Okay? For complicated loss functions, and especially loss functions that involve multiple variables, I won't be able to draw for you the loss curve like this. But the same idea applies when I move from 2 dimensions to 3 dimensions, and from 3 dimensions to p dimensions. Okay. And so this kind of gives us an idea for an algorithm to minimize the loss. Okay, so instead of finding this loss using calculus, what we can do is we can say, okay, let's just start theta somewhere. So maybe we'll start it at 12. And we'll just keep nudging theta until it stops moving. And the way we'll nudge it is we'll nudge it towards the positive direction if the gradient is negative, and we'll nudge it towards the negative direction if the gradient is positive. Okay, so for example here, we're going to nudge it to the left. We might nudge it to the left again. And maybe by the time we nudge it a few times, we'll get close to the bottom of this loss curve. And if we do so, then we'll get a value of theta that's pretty close, maybe not exactly, but very close to the real minima of this function. Okay? And again, once you find the theta that minimizes the loss curve, you fitted your model to the data. You found theta hat. Okay. So gradient descent. The idea is to nudge theta in a negative gradient direction. And so to write that mathematically, we'll write down this equation here. Okay, so this is simply the idea that I described to you on the previous slide, written down in a mathematical equation. Here's how you read it. We have theta with t plus 1 here. So this is not an exponent. When I write parentheses t plus 1, I'm just referring to theta at the next iteration or next time step of gradient descent. Okay, so right here I have the next value for theta on the right-hand side, and I'm saying that to compute the next value of theta, we'll take our current value of theta, look at the gradient, and subtract the gradient. This alpha here is called learning rate, and we'll set that to a smaller constant. Okay, so usually it's like something small, like 10 to the negative 3. But basically the idea here is we'll take a small step against the gradient of a function, and that gives us the way that we can set theta to a new value that's better than the one before. Okay, so here's the notation. Theta are our model weights, L is a loss function, alpha is a learning rate, Y are the true values in the training data. Okay. So here's the algorithm. We can initialize the model weights to all 0. Sometimes you'll also see people initialize the model weights using small random numbers. Depending on the model you're using, doing one or the other can help. Then we'll update the model weights using this update rule, which I had in the previous slide. And we'll repeat that process until the model weights don't change too much, which signals that we're converging on the minima of that loss function. And that's pretty much it. That's gradient descent. Okay. So let me show you an example using the mean squared error loss. Okay. Oh, and again, I had a few questions yesterday about the difference between theta and theta hat. Okay, so the difference between theta and theta hat is that theta refers to our model parameters in general, and theta hat refers to the set of model parameters that minimize a particular loss function. In other words, let's treat our model as a box with some knobs to tune, right? So we have some knobs on our box, and if we turn those knobs, we get a different loss, okay? So theta refers to like the configuration of knobs, and theta hat refers to the very specific configuration of knobs that minimize our loss. Okay, so when I say theta and theta hat, they really refer to the same thing, but theta hat is a special version of theta. It's the version of theta that gives us the minimum loss for a particular loss function. Okay. So let's talk about gradient descent for the mean squared error loss, and let's use a constant model. Okay, so if you have a constant model, our loss is the following function of theta. So again, I have the error for every point, squaring all the errors, taking the average of all the squared errors. This is the mean squared error loss. The gradient of this function with respect to theta is this one right here. So again, this loss is single variable, so the gradient is a simple scalar here. So this right here is a single number that tells us the slope of that function. Okay? And so we can write the update rule as this. So I've taken the gradient descent update rule, and I plugged in my gradient loss into the gradient L that I had in the previous slide. So this is a procedure you should become familiar with. Okay, so if I tell you to write the update rule for a loss function, you should be able to say, okay, well, what I need to do is take the gradient, plug it into the loss function, and maybe simplify a little bit if there's some complicated terms going on in here. That's about it. And it's much simpler, like algebraically, than setting the loss equal to 0. Right? So before we set the loss equal to 0, which means we have to expand out the sum and like move terms over to the other side and then do some division and then like simplify from there. And doing this and just taking the gradient here is usually much simpler mathematically or algebraically than taking that gradient and setting it equal to 0 and then solving for theta, which is what we had to do before. Okay, so let me show you how this works. Go. Okay, so let's say I have 5 points. Here are my 5 points on the x-axis. And what I've showed you before is I can write the MSE error, MSE loss, and I can check the loss values for different values of theta, right? So I can say, okay, if I set theta equal to 14, what's my loss? If I set theta equal to 15, what's my loss? So on and so forth. So I'm going to do that. And we see here we get this curve. And if I try out a lot more thetas here, I can fill in the spaces in this curve to get a smooth curve. All right. And so let's say that we start theta at 12. Okay, so let's say I initialize theta, and just for demonstration, I'm going to say let's start at 12. What I want to do here is write down a function that computes the gradient of the loss. And the gradient of the loss that I just derived for you is -2 times the mean of my y values minus theta. That's the gradient. Okay, we can write the update rule for gradient descent. And the update rule for gradient descent is the original value of theta minus alpha times the gradient of the loss for theta and y values. Okay. And that's about it. Okay, so if I call gradient descent 1 on, let's say, so my starting value was 12. If I set gradient descent 1 equal to start, my original points, and use the gradient MSE function, I see that after running gradient descent for one step, this tells that I should change theta from 12 to 13.6, which is closer to the lowest loss possible. Okay. So what I'm going to do now is just show you a few more steps of that. So I have here a function that'll show me a few more steps. So let's plot gradient descent like so. Okay, so this is one step of gradient descent. I started out with 12, and I moved theta to 13.6. Okay, let's run it again. Change the start here to 13.6. And we see that we moved from 13.6 to 14. My Siri got activated. Okay. 14.2, let's run it again. 14.2, now it's 14.5. Run it again, 14.6. Okay, so I can keep doing this, right? 14.63, 14.65, right? And I keep doing it. So you notice that as I run it more, my theta changes less, right? My theta changes less because the gradient gets closer and closer to 0, which means that my update is not as big as it was before. And so naturally, via this loss function and using the gradients, we'll start by moving theta quite a bit in the beginning, but as we get closer to the minima of the loss function, we'll move less and less until we get almost no change at all in our theta, and that's when we'll say we'll stop running gradient descent, and we'll call that our theta hat, our minimizing model weights. Okay? And again, for reference, remember from before that the actual mathematical minima of this loss function is the mean of my points. And we got 14.66, which is pretty close to the theta that I would have gotten from gradient descent. Okay, so we can confirm that the two match each other, which is good news. Yeah, Frederick?
So are we using gradient descent on the same data set, or we can use in different data set? What if like we switch another data set, give us different, data for the slope of the model? How do we determine which one is needed?
So the question is, if I switch data sets, what happens?
Yeah.
And if I switch data sets, really all I need to do here is change the points variable to a set of new points. And gradient descent will still run because the mean squared error loss function will always look like a little bowl here.
Yeah, so how do you determine which one you want to use for the minimal value for data?
How do I determine which theta how do I determine when to stop gradient descent? Is that the question?
Yeah, like you have the test set and then you use gradient descent to like which test set you want to choose to find the minimum data value.
I'm not super sure what your question is, but if I want to change my data set, if I'm trying to run gradient descent on a different data set, I need to change this points variable here to point to some different data values. And whenever I change the points variable here and run gradient descent until it converges, then I will get the minimizing theta for that particular data set. So if that didn't answer your question, we can talk during the break or after class. Okay, that's gradient descent, that's the algorithm. And you may notice here that as long as I define the gradient MSE, I can run gradient descent on pretty much any loss function that I choose. Right? So if I swap out the MSE with the MAE, the mean absolute error, I can still run gradient descent. Or if I swap it out with something more complicated, it'll still take this ball and roll it down the hill until it gets to the bottom of the bowl. Yeah, Danny?
Do we keep the learning rate like a specific constant, or do we need to decrease it over time for convergence?
We're going to talk about that right now. But in general, in this class, we won't do anything super sophisticated with the learning rate. But other times, you'll hear an adaptive learning rate, which means that over time they decrease that learning rate. Okay, so let's talk about the learning rate, which is this constant alpha here. It's called the learning rate because it adjusts how fast gradient descent converges. Okay, so it adjusts how fast your algorithm learns. So if you set alpha to be a higher value, you're going to take a bigger jump, right? You're going to move theta more at every time step. In theory, that will cause your gradient descent algorithm to converge in fewer steps. But if you set alpha too high, gradient descent may actually never converge. Okay? If you set alpha too low, gradient descent will take a long time to converge because you're not going to move theta too much at every time step. Okay, so let me show you what happens. Right, here we go. I have a function here that just plots several iterations of gradient descent. And what I can show you is before alpha is 0.3. So if I call this, let's plot these iterations. Let's plot 4 of them. Here's my points, starting value, and let's say 0.3. So here's my alpha, 0.3. Let me just put alpha here. Okay, this is the same algorithm that I just ran up above. So it decreases like so. If I change alpha to 0.6, this green dot will move over to the right more so, right? Because I'm going to be taking a bigger jump in the positive direction. So here it is. It's a bigger jump. And each of these steps is a little bit bigger than the one before, or the one from the previous alpha value. And we converge a little faster than the one before. Now watch what happens if I set alpha to be a large value. Let's say I set alpha to be equal to 1. Okay, so first theta is here, now it moves here, now theta moves back here, and now it moves back here. And so why did that happen? It's happening because I set alpha to be a big value, which means we're gonna push theta in the positive direction. But if you push theta too much, it'll end up right back where it'll end up like more or less where it started. Okay, so we're gonna end up with theta back here, and this right here will flip-flop back and forth endlessly. It will never converge. Okay. Now, in reality, you won't often encounter this. What's more common is that you'll encounter the following case, where let's say I change my starting value to 14, and I set my alpha to something pretty big, like 1.2. Okay, so here's what you'll encounter in real life, which is you may start your theta at a low loss value, but you notice after the first iteration that your loss increases. Right, so my first iteration, my loss increased a little bit, and I run gradient descent one more time, and it jumps over here, and now I have a bigger loss value, and now I have a bigger loss value, and now I have a bigger loss value, and if I run this gradient descent, if I run this algorithm for like 100 more iterations, I'll get like a gigantic loss value. Okay, so the learning rate is your friend and your foe. You can use it to tune how fast your algorithm converges, but you tune it too far and make it too big, and your algorithm will never converge. That's one of the drawbacks of gradient descent, is trying to pick the right alpha. Okay, so how do you determine whether gradient descent is working or not? What you should normally do is print out your loss values as you run your algorithm. And if you notice your loss value is getting way bigger than they were before, that should signal to you that you turned alpha too high. Okay. And again, in this class, alpha will usually be a small constant. So for this particular demo, I set alpha to be like 0.3. In real life, that's like really big. So in real life, what's more common is like alpha of like 10 to the -4 or 10 to the -5. It kind of depends on your data set, but usually alpha values are pretty small. And in this class, we're going to set alpha to be the same for all iterations of gradient descent. But you may also see, and it's pretty common to use what's called an adaptive learning rate, which essentially means you start alpha at a big value, and then as you have more iterations, you make alpha smaller and smaller as you go. And so when you do that, the idea is like you want to start off with some big steps, but as you get closer to the minimum of your loss function, you want to take smaller steps so you can actually hone in on that minimum. Okay, all right, why don't you try it out? So derive the gradient descent update rule for a linear model with 2 model weights, no bias term, and the MSE loss. And you can start by taking the gradient for a single data point. Okay, so here's the model. Here's the loss function for a single data point. And what I want you to find is the gradient of this loss function. Okay, so you'll see me use little lowercase l and capital L. When I write lowercase l, I'm referring to the loss for a single data point, and capital L means the average loss for a data set, usually, unless I say otherwise. Okay, so in this case, I just want you to find the gradient for a single data point. It turns out that once you have the gradient for a single data point, finding the gradient for a whole data set is not too hard. What you do is you take the average of the gradients for all the original points. Okay, so the gradient of big L is the average of all the gradients of the little l's. Okay, so try it out now. It's a little harder, so take your time. And then after a few minutes, I'll have you talk with your neighbors about what you got. Okay, so even if you're still working on that problem, why don't you talk over with your neighbor on the progress you currently have, see if you can help each other make some progress on this. All right, so let's bring it back together. And again, asking these sorts of questions is like super easy for an instructor for a course to put on the exam. So if you see this type of question like in class for another class, you should think to yourself like, what could the instructor do to ask me a question like this on the exam but not exactly this question? And the way that I would do this is I would change the theta 1 to theta 1 squared. I would change the x2 to x2 squared. Or I would change the x2 to a log of x. Okay, so many types of variants from this question, and you should be able, if you want to test yourself, you can try changing up the parameters on this function here and trying to see if you can still find that gradient. Okay, so super easy to do, super easy to include a question like this on the exam. I'm not saying that there will be one, but I'm saying that it's easy for me to do so, so maybe there will be. Okay, so here's my loss. Oops, there wasn't supposed to be a summation. I do apologize. So pretend that summation is not there. Okay, so the gradient with respect to theta 1, or the partial derivative with respect to theta 1, is you take this term here, you move the exponent down, apply the chain rule to theta 1, and you have negative x1 multiplied. Okay? Similar logic applies for theta 2. So again, the exact same term here, but with x2 instead of x1. Okay? And the gradient of that loss is the two partial derivatives stacked on top of each other. And that's what I was looking for, really. If you got that, I think you should give yourself a pat on the back, because that was pretty good. Okay. Now it turns out that once you have this formula, you can actually run gradient descent on the data set as is. So if I told you fit a linear model to some data, there's two model parameters, and you don't need to care about the intercept, you could just write this in Python and run gradient descent. And the way you run gradient descent is you would compute this for every point and then take the average of all the gradients. And that will let you run gradient descent on the whole data set. But of course, I won't be satisfied with this just yet. And the reason why is because I usually want you to write the gradient in matrix form. Okay? So if I have this gradient as a vector, what I can notice is I can start replacing the parts of the gradient with some vector products. All right? So I notice that this theta 1 x1, theta 2 x2 is the dot product of theta and x. So I can replace these terms with theta dot x and theta dot x here. And I notice that y sub I minus a dot product is a scalar. Right? It's not a vector. This term right here is not a vector. It's a single number because y sub I is a single number. It's a single training point of my data. And the dot product of two vectors is also a scalar. So I have here a scalar on the left-hand side, which means I have a scalar times x sub 1, a scalar times x sub 2, which is equal to a scalar times a vector x. Okay? So I replace this term right here with the dot product, and I notice here that this looks a lot like the vector x, so I can replace this with the vector x. This is something that you should be able to do, but if you only got this far today, don't worry about it. I think that's totally fine. But you should practice taking these gradients here in vector form and converting them to some vector dot products instead of having to stack together a bunch of equations. Okay, so again, -2 is a constant, yi minus theta dot x is a constant, and x is a vector, a p by 1 vector. Okay, so we get the final result is p by 1. Once you write the matrix form, or once you write a gradient in matrix form, you can naturally extend your logic to any number of dimensions, right? So in my original formulation of the problem, I asked you to do it for 2 dimensions. And it turns out that once you do it for 2 dimensions and then write down your product in vector form, this actually works out for any number of dimensions, not just 2. Right, so if I ask you a question of derive the gradient descent rule for p dimensions, and you're confused as to how to approach the problem, one way to simplify the problem is to say, okay, well, instead of working with p dimensions, let me just work with 2 dimensions, and then I know I can generalize back to p dimensions once I have it in vector form. Okay. Now, the overall loss is I'm going to take this formula here and upgrade my terms. Okay, so if I want to find the gradient of, if I want to find the average gradient of all the points instead of just 1 point, I'm going to upgrade my terms. I'm going to upgrade my little x here to the matrix x, upgrade my y sub I to the vector y, okay, and my row vector x becomes a vector in the matrix x sub I, and this y sub I stays the same here because I'm doing the summation over rows of my input data. Okay, so once you have the loss for a single point, finding the overall loss is not too bad. You essentially put a 1 over n and a summation in front of the single point loss. Okay, now it turns out that you can simplify this even more. You can actually simplify this down to this this matrix multiplication here. But if that's really stressful for you, don't stress out too much over it. I will expect you to know how to do this on the top, but not the matrix simplification, because a matrix simplification is pretty hairy to do. But you should be able to prove to yourself and also demonstrate that the formulation on the bottom here is the same as a formulation on the top for a matrix instead of a vector. So if I ask you to work backwards, you should be able to work backwards, but you don't have to worry too much about going forward. So if you don't have to worry about going from here to here, but you should be able to go from here and show that this right here gets you, like this matches the loss for a single point up here. Okay, but again, the reason why I write it in this form here is because once you have the loss in terms of matrix multiplications instead of a summation, your code will generally run much faster. Okay, so if you can write your gradient descent rule like this, instead of like this with the summation, chances are you'll just finish fitting your model a lot faster than you would otherwise. Okay, so here's an update rule. Here's my gradient. Here's gradient descent. Plug the first row into the second row, and I get this. Okay, so this is the update rule. And again, so because I have this in matrix form, this works for any number of variables. So we've actually derived the gradient descent update rule for a multivariable linear model, okay, with any number of dimensions and any number of rows. Okay, so let me show you how this works. Here we go. I'm going to use the SciPy minimize because I want to save the gradient descent. I want to save the real gradient descent implementation to you guys during lab. So I'm not going to give away the answer. I'm just calling another minimization function. Here's my MPG data set from yesterday. Okay, And let's say that I will use all my numeric columns to predict MPG. So I have here my columns. I have here my matrix X, which is my training data. So here's my training set. And then Y here are my training true values. Okay? All right. A linear model is, if you remember, X times theta, right? The matrix X times the vector theta. Okay? The loss of a linear model is the mean of my Y values minus my predictions squared. The gradient, I brought a return that. Okay? The gradient of my loss we derived on the previous slide. I don't expect you to memorize it, but again, it is -2 divided by n times x transpose times y minus x transpose times x times the thetas. So complicated, but again, I'm just directly translating the math on my slide into Python. Okay, so once I have these pieces down, I can fit my linear model by calling the minimize function. Call it on my MSE loss, grad MSE loss, and just pass in x and y. Okay. And here's what happens. So it's harder to visualize because I have many dimensions. But here I'm starting off theta. The first row is supposed to be all zeros, but this is showing the second iteration and onward. But here is showing how it's updating theta as gradient descent moves on, and my loss decreases until I get to a loss of 11.59. Okay, so here are my finishing theta values. So gradient descent updates all my thetas at the same time, right? Because the gradient is a p-dimensional vector, and theta is also a p-dimensional vector. Okay, so whenever I perform one update of gradient descent, I'm updating every theta value at the same time once. Okay. So what I can do here is I can compare, again, the gradient descent solution with the matrix inverse solution that I showed you yesterday. And those two get the same result. So good job, gradient descent. And I can show you that they have the same, they have the same theta, so they have the same loss. And what I can do here is show you a peek at what gradient descent is doing. And the way I'm going to show you a little bit about what gradient descent is doing is if I only have two columns here, the bias and the horsepower. So I'm fitting a single variable linear model using horsepower to predict MPG. And I can call my thetas. I get the following thetas. It converted after 4 iterations. And what I've done here is I have skipped ahead, put the thetas into an array, and I can show you how the best fit line changes over time as you run gradient descent. Okay? So first, after the second iteration, we have this line here. We run gradient descent and update both the slope and the intercept at the same time. We get this line. Okay, run another gradient descent iteration. We get this line, so it's getting closer. Run it again, we get this line. Okay, so this right here would be the best fit linear model for these two variables. Okay, so we start off with a dumb theta. We start off with a theta of all zeros. Okay, but gradient descent changes those thetas in an intelligent way so that we eventually recover back the best fit line for this particular graph. Okay, let's take a break. All right, and we'll come back in 2 minutes. We have a bit more material to go through. Okay, let's bring it back together. Is anyone still filling out attendance? All right, keep it open for a few more minutes. And I want to talk to you now about what we call stochastic gradient descent. Okay, so we saw in the previous gradient descent algorithm that at every update of theta, we're going to update theta using the average gradient for all the data points. And it turns out that there's a version of gradient descent where instead of taking the average across all the data points, you just take a single data point and make an update using a single data point. Okay, so what we call batch gradient descent is the algorithm I showed you in the previous slides, where we use capital L to refer to the average loss across all the data points. And what we call stochastic gradient descent is if I make an update, but only using one point at a time instead of all the points in my data set. Okay, so it appears to be, it appears less sophisticated, but actually stochastic gradient descent usually converges faster than batch gradient descent when it comes down to real data. Okay, so actually, if you see gradient descent used in the real world, almost all the time they're referring to stochastic gradient descent and not batch gradient descent. Okay, so the algorithm for gradient descent, or for stochastic gradient descent, is very similar. Okay, so again, initialize the model weights. Instead of taking all the input data, we'll shuffle it. And for every point in my shuffled input data, we'll perform an update. Okay, well, we'll do this update rule. And we'll repeat steps 2 and 3 until theta stops changing, until we reach convergence. Okay, so I do want to point out that every time we update theta, we'll call that an iteration. And every time we pass through the data, one full loop, we'll call that an epoch. Okay, and the reason why we differentiate between these two is because it allows us to better compare stochastic gradient descent with batch gradient descent. Okay, so batch gradient descent, every iteration is also an epoch, right? Because every time it updates theta, batch gradient descent will loop through all the data points. In stochastic gradient descent, if you have 1,000,000 data points, you're going to make 1,000,000 updates until every time you run through the data once. Okay. So for example, here's the update rule for the constant model and mean squared error loss for batch gradient descent. This is what we derived a few slides ago. And the stochastic gradient descent rule looks very similar. Okay, so again, all I'm doing here, more or less, I'm just removing the 1 over n and a summation, and I have the stochastic gradient descent rule. Okay, so the two are very similar. You don't have to do any more sophisticated math, really. You're just removing the average from batch gradient descent. Okay. And so I mentioned before that stochastic gradient descent performs better than batch gradient descent in practice. I have a demo. What demo do I have? Oh, I do have a demo. Oh, great. I forgot I had a demo. All right, how exciting. Okay, cool. So I'm going to show you the stochastic gradient descent on this familiar loss function. Okay, so I have here, I have to write a function that takes the gradient at a single point instead of all the points. But it looks very similar to the gradient for a single point minus theta. That's pretty much it. And here is my plot. I'm going to plot an epoch of stochastic gradient descent. And here's what happens. Okay, so the first iteration, theta moves down here. Second iteration, it moves down here. Third iteration, it moves here. Fourth iteration, it moves up the loss curve, kind of weird. And then the fifth iteration, it moves back down. Okay, so we notice some interesting behavior, right? The interesting behavior of stochastic gradient descent is that sometimes it moves towards higher loss instead of lower loss. Why might that happen? It might happen because, depending on how my points were shuffled, I might be comparing theta to the point that was at, let's say, 16. Okay, so because stochastic gradient descent is only comparing theta against one point at a time, depending on where the point ends up, you might move away or towards the region of lower loss. So you can think of, for the constant model and for this very simple case here, you can think of a stochastic gradient descent as saying, okay, well, take all my points and shuffle them, and then loop through all my points, and every time I get to a point, I'm going to move theta towards that point. Okay, so here theta moves towards a point on the right-hand side. Again, the point is on the right-hand side. Here the point is on the right-hand side again. But here, the point that got shuffled ends up being on the right-hand side of theta for this iteration. And then here, the point's on the left-hand side, so theta moves back. Okay, so interesting behavior, and it seems non-optimal, right? Like ideally, we move theta towards the minimum loss at every iteration, and that feels to us like the best way to get theta to be as small as possible, as fast as possible. But in reality, it turns out that stochastic gradient descent actually performs well, and oftentimes better than batch gradient descent. And the kind of intuitive reason why this happens is that stochastic gradient descent does more with each data point. Right? So if I have a sample of size 1 million, every update for batch gradient descent will require at least a million calculations, right? One for every data point. Whereas stochastic gradient descent will have updated the weights 1 million times by the time batch gradient descent does one update. Okay, you can imagine that the collective effort of those 1 million points eventually just gets theta closer to the minimum than batch gradient descent, because batch gradient descent will only nudge theta a little bit, whereas in stochastic gradient descent will move theta quite a bit, and eventually theta will end up near the minimum. Okay, but you do have to know that batch gradient descent will always move towards the optimum. It'll always move in the direction of lower loss, whereas stochastic gradient descent will sometimes move away because it only considers 1 point at a time, as I showed you on the demo. Okay. So again, here's a visualization of batch gradient descent. This type of plot is called a contour plot. And in this case, what I'm showing here is, it's like a kernel density estimation plot, but for a function. Okay, so here I have two model weights, theta 1 and theta 2. And this darker circle here is a region of lower loss, and the lighter circles are regions of higher loss. Okay, so the lighter you are, the higher loss, and the darker you are, the lower loss. And our goal is to get to the point of lowest loss. So if I run batch gradient descent, we'll always move in the direction of lower loss. Or as stochastic gradient descent will kind of make a meandering path and eventually get there on average. Okay. But you may notice here, but what this diagram is trying to illustrate is that here it took me like 7 iterations to get something pretty close to my optima. For batch gradient descent, it took 7 iterations, but each of those iterations required like an entire pass through all my data at the same time. Okay. And what you may notice in real-world data sets is that if your data set is very large, sometimes stochastic gradient descent converges even before you look through all your data. So if you have like 1 billion points, stochastic gradient descent can actually converge after only looking through, let's say, like a couple million of them. Sometimes. Not always, but it is able to do that. And again, the idea is that it does more with each data point, or if each data point is redundant in some way, stochastic gradient descent kind of ignores that redundancy or deals with that redundancy in a better way. Okay, so that's SGD. Talk about convexity. Turns out that gradient descent is not a super magical algorithm. Okay, so it turns out that gradient descent is not guaranteed to find the global lowest loss. It's only guaranteed to find the local lowest loss. And what that means is if we have this loss curve that looks like this, we notice here that we have a local minima of loss right here, but the global minima of loss is way over here. It turns out that if I start theta at this value and run gradient descent, here's what happens, right? We're going to move from here to here, and then here to here, because the slope here is positive, right? So theta will move negative, and then we're going to move from here to here, and we'll actually never end up at the globally optimal loss. Okay, so this is what we call local minima problem. And so gradient descent can converge at 15 when the global minimum is 18. And it turns out that gradient descent can be arbitrarily bad. And when I say gradient descent can be arbitrarily bad, I mean that I can take this loss right here and just like stretch it down towards like as far low as I want it to go, right? And gradient descent will never see that loss if it ends up in this local minimum over here. It can end up in a really bad spot, basically. Okay. Now it turns out that we don't like to work with these types of loss functions because of this property. And in particular, we like to work with what we call convex loss functions. Okay, so a convex loss function, for a convex loss function, any local minima is also a global minima, which means that when gradient descent converges, you're guaranteed to find the global minima for that loss. Okay. Formally, we write this, and if this inequality holds for the function f, then the function f is convex. And this is intimidating, so let me translate this to English. In English, this means that if I draw a line between 2 points on a curve, all the values on the curve need to be on or below that line, which means here's an MSE loss. I can draw a line between 2 points, and I notice that the line is above the curve always. And that's essentially what it means to be convex. Okay, so no matter where I draw the two lines, no matter where I connect the dots, the curve will always be below or equal to this line, and that's the definition of convexity. Likewise, this function is not convex, right? Because if I draw the line here, the curve goes above the line, and so the function is not convex, and gradient descent is not guaranteed to find the best minimizing loss. Okay. So we've gone over the basic gradient descent algorithm, and we've gone over some considerations for gradient descent. One consideration is changing gradient descent to be a stochastic algorithm. The second consideration is convexity. And the third consideration is the loss function that we choose for gradient descent. Okay? So oftentimes, we actually pick a loss function that behaves well for gradient descent. For example, the mean squared error loss has larger gradients when you're far away from the minimum. Right? You saw how it was a bowl shape for the plots I was showing you before. And what that does for gradient descent is it lets gradient descent make large steps at first, and then make smaller steps as you get closer and closer to that bottom of that loss curve. Right? The mean absolute loss, however, is not differentiable at its minimum. And so actually, for the mean absolute error, gradient descent will seldom truly converge to that minimum. Here's what happens. Okay, so if I have this MAE loss, what I've done is I've taken the same data set that I showed you before, but I've replaced out the mean squared error loss with the mean absolute error. So gradient descent will kind of hop over to this side, but when you run gradient descent again, it'll hop back over to the other side. Because the gradient is the same both here and here, it doesn't get gradually smaller as you get closer and closer. So what happens is when you get down to the minimum of MAE, gradient descent will actually just kind of hop back and forth and never really converge. So you do have to be careful when you're picking loss functions. It's usually good to pick a loss function that's differentiable everywhere. And so you may ask the question, well, I like the MAE because it's robust to outliers, right? So the minimizer for this function is the median, and we like it because even if we have outliers in our data, the estimation will still perform pretty well. And it turns out that there is a smooth version of the MAE, which is called the Huber loss. It looks like this. It's intimidating. But how you should read this is the top part here looks a lot like the mean squared error loss, and the bottom part here looks a lot like the mean absolute error. Okay, so what happens for the Huber loss is that when the points are far away from theta, it behaves like the mean absolute error, so it's robust to outliers. But when you get close to the bottom of that loss curve, it looks like the mean squared error loss, so it's smooth, and it decreases gradually. Okay, so as pictorially, here's what the loss looks like. It's linear when theta is far from the point, but then when you get down to the bottom here, it's smooth. And the nice property here is that it's differentiable everywhere. Okay, So delta here is a parameter of the loss. You should play around with delta, and I show you some examples of this in the textbook as well. But it turns out that for this loss, there is no analytic solution. Okay, so you can't, or none, no simple one. So you can't just solve it and get the mean or the median of the data. But instead, we'll use gradient descent. Okay, so what you should try doing is taking the derivative of this loss function and try running gradient descent on it for practice, working with loss functions and derivatives. Okay, and I show you Huber loss to illustrate the point that sometimes we'll pick a complicated looking loss function because it behaves well for gradient descent, knowing that once you find the gradient once, you don't have to rederive the gradient every time, right? So once you know the gradient for Huber loss, you write that Python function for the gradient, and now you can use it forever. Okay, and so because of that, we'll often choose a loss function that looks pretty complicated, but behaves well for gradient descent, knowing that we only have to take the gradient once. All right. So gradient descent works in many models and loss functions as long as you can take the gradient. It's usually much easier to take the gradient than to solve it. It also finds a solution faster than the analytic solution, sometimes if there is one. So the normal equations for linear regression run too slowly. Instead, we use gradient descent. Okay, so our modeling recipe is to pick a model, pick a loss function, and fit that model by running gradient descent. And that's what we'll do from today onward. So we're going to be talking about all sorts of models. We'll talk about ridge regression. We'll talk about lasso regression. We'll talk about logistic regression. And for all of those cases, we'll just use gradient descent to minimize all of them. Okay, so if you remember this diagram I showed you in the very first lecture, we've gone through all of it, right? We've gone through formulating a question. We've gone through the process of cleaning data. We've gone through the process of exploring that data and visualizing it to draw some conclusions. And after we do these three steps, we've gone now through the foundations of the fourth step, which is making some inferences about the population and making some predictions using our data. All right, that's all I got. I'll see you tomorrow.